Okay, so we're continuing with this note after system of equations by now talking about how two planes can intersect and how we can find how they intersect. Okay, so two planes can intersect in three different ways. Either they can intersect along a line, as shown beautifully in the first photo. They can be two parallel planes, or they can be coincident planes. There actually is no way for two planes to intersect at a single point. These are the only three options. So notice that parallel planes and coincident planes will have normals that are scalar multiples. So this is important because really we should check first before we go ahead and actually try to find a line of intersection to see if they could be parallel or coincident. It will save us a lot of work. So if the normals are not scalar multiples of each other, it has to be a line of intersection. So I'm going to show you how to use this to find what the actual equation of that line is. Okay, so example 1, find the intersection between these two planes. So we'll call this one plane 1 and we'll call this one plane 2. So notice that the normals are normal 1 is 1, -1, 1, and normal 2 is 1, -1, 1. So therefore, these planes, like not even just scalar multiples, it's flat out normal 1 equals normal 2. So therefore, they're parallel or coincident. Okay, so we have to figure out which one it actually is. So take a look. You should be able to just think about it just by looking at these two equations and think, well, if these values are different, then they have to be parallel and not coincident. But I'll show you what happens when you actually try to solve this system. So let's say I want to add the two equations together to eliminate a variable. So let's say I multiply equation 1 by -1 to get -x plus y minus z equals -4. And I add that to plane 2, which is x minus y plus z equals 5. So check out what happens. You get 0x minus or plus 0y plus 0z equals 1. So notice that there are no solutions to this system. Okay, no matter what x, y, and z you choose here, you'll never be able to get 1. So therefore, that means that they are parallel planes, not coincident. Okay, so what happens here with this example 2? Okay, so again, we check the normals. So normal 1 is equal to 1, 2, -3, and normal 2 is equal to 4, 8, -12. So notice that normal 2 is just equal to 4 times normal 1. So therefore, these are parallel or coincident. So you can just take a look at the constant. Okay, here it's -1 and here it's -4. So that constant is multiplied by 4 as well. The same scalar that we use to multiply the normals can also be used to multiply together to get those constants. So that's how you can tell these are coincident and not parallel. But watch what happens when you try to actually solve the system. If you try to solve it, okay, so actually, I should just write that. So note that our D1 is equal to -1 and our D2 is equal to -4. So therefore D2 is equal to 4 times D1, which follows the same K as over there. So the entire equation 2 is equal to 4 times the entire equation 1. So that's how you know they're coincident. Okay, The other way is if you actually try to solve this system, you'll result with 0x plus 0y plus 0z equals 0. So there are infinite solutions to that system because anything you put in for x, y, and z will satisfy that equation. So that's how you know they're coincident. Okay, let's go to what happens if there's a line of intersection. How do we find that line? Okay, this is a bit more abstract. I'm going to warn you. There might be a little step in here that you're uncomfortable with. I'll do my best to explain why it works. But if you're still having trouble, make sure you talk to me in class. So our first normal is 1, -1, 1, and our second normal is 2, 2, -2. So it looks like they could be scalar multiples, but they're not. Okay, so they are not scalar multiples, so must intersect along a line. Okay, so what we're going to do is find the equation of this line of intersection. So I'm going to lay out the steps for you, and hopefully you're able to follow them so that you can imitate them in similar questions. So the first thing we're going to do is we're going to remove x. Okay, so we're going to multiply equation 1 by -2 to get -2x plus 2y minus 2z equals -6. And we're going to add that to equation 2, which is 2x plus 2y minus 2z equals 3. And so that eliminates. We get 4y minus 4z equals -3. So we're going to call that equation 3. Okay, now this is where you are going to maybe get a little bit uncomfortable here, is we're going to, so step 2 is we're going to introduce a parameter. You're like, what are you talking about? I mean, maybe that's what you think most of the time, I don't know. We're going to introduce a parameter, okay? So we're going to let z be equal to, that's a z, be equal to s in equation 3. All right, I get that this seems like, but what, how can you do that? Basically, we are creating a point by letting z equal s. That is what z is going to equal in the parametric equation. Okay, so essentially we're finding a point where z is 0 because this is 0 plus 1s. And we're finding the direction vector whose z coordinate is 1. And we can do that because the direction vector can be scaled to anything. So again, we're finding the point where z is 0 and the direction vector where the z coordinate of that direction vector is 1. So we're just, because the solution, or sorry, the equation is not unique, we can do that. All right, that might be confusing, but let's just go with it. So we get 4y minus 4s now equals -3. And then we're going to change that to y equals s minus 3/4. Okay, so we've just rearranged. All right, I hope I have enough room. On my sheet I do, but on this with the trackpad, I don't know. So step 3 now is to sub z equals s and y equals s minus 3/4 into equation 1. Okay, so you get, I'm going to use a different color just so it doesn't get lost here. So you get x minus s minus 3/4 plus s equals 3. So now we can rearrange x in terms of s and numbers. So when we do this, s actually goes away, which doesn't have to happen, but in this case it does. So we get 0s plus 9/4, okay, or just 9/4. So then step 4 here is to write the parametric equation. So we get x equals 9/4, y equals s, or -3/4, we can say, plus s, and z equals s, where s is the parameter. Okay, so if we wanted the vector equation of a line, the coordinate then is 9/4, -3/4, 0, plus s, and then the direction vector is 0, 1, 1, where s is in the set of all real numbers. Okay, that's a bit of a complicated example. It's a little bit weird with just introducing that parameter. It's going to take you guys some practice until you're comfortable with actually implementing that. Okay, so then you can see another example on page 513. I recommend you go and check that out. Okay, last example is determine the equation of a line that passes through the point 5, -2, 3, and is parallel to the line of intersection of these two planes. So notice that our ultimate goal here is the equation of a line. So the equation of a line, remember, is just R equals RO plus TM. So really what we need is a point on the line. Well, hello, we already have one. And the direction vector on the line. Well, because the line is parallel to this line of intersection, this direction vector will be, you guys can I'm just finishing up a video. Yeah. Just close the door. Okay. This direction vector will be the same as the line of intersection between these two. Okay, so we're going to actually find the line of intersection then. So we need to find the direction vector and the line of intersection. That's all we really need to be able to answer this question, because we already have a known point. Okay, so we're going to so notice that in pi 2, x is already eliminated. So we don't even actually have to do step 1. We can go right to step 2. So we're going to let z equal a parameter. Let's do t this time in equation 2. So then y is equal to 1 minus 2t. All right, so then we can sub that into equation 1. So you get x plus 2 bracket 1 minus 2t minus z, so minus t equals 6. And if you rearrange for x, you get 5t plus 4. So therefore, these are the parametric equations. There's one parametric equation, there's the other parametric equation, and the third parametric equation. So the vector equation is the x coordinate from here, which is 4, the y coordinate, so 1, and here it's 0, plus t. Now the direction vector in x is 5, and y it's -2 and 1. So here we have it, folks. This is the direction vector of the, the line of intersection. So our required line is parallel to that, so it has our same direction vector. So therefore, our required line is R equals the point that it goes through, so 5, -2, 3, and t 5, -2, 1. T is in the set of all real numbers. Now, there's actually another way of doing this question, which involves the cross product, but it's a lot more visual, a bit more complicated to understand. It's on page 514. It's actually method 1 in the textbook. I presented method 2, but I encourage you guys to check it out. Okay, so as you know, there's students waiting at my door, so I gotta go. Thanks for watching. Hope you learned lots.